Welcome to the optical communication course. So today we will see that a SONET and SDH. That SONET we say that it is nothing but a synchronous or optical network, and SDH is nothing but a synchronous digital hierarchy. Now, if you compare that a SONET and SDH, as we mentioned that SONET and SDH these are nothing but a standards used for the transmission format or a transmission packet transmitting through this optical network. So now if you see that the basic structure of this SONET is it has a 90 bytes, 90 columns of a bytes there, and that 90 columns of a byte consist of 87 columns and a 3 columns there. And out of that 87 columns, if you see that it consists of synchronous payload envelope and a path overlay, and a 3 columns consist of section and a line over area. Now this structure, we say that it has a 90 columns and a 9 rows of a byte, and you know that that byte is nothing but the 8 bit. Now in this SONET we use, if you see that it has a 3 columns, and a 3 columns consist of section and a line over it. Section is used to connect the adjacent pieces of equipment, and a line is a link that connects the two SONET devices. So that is about, we can say here, the terminology of a SONET. And a path is nothing but, it is nothing but a end-to-end connection between the node, or that is a through the link. So that's why we use a line, section and path in a network here. Now if you see the SONET frame, in a SONET frame, they it takes a 125 microsecond of a duration. So that is a transmitting the signal, and the transmission bitrate of that basic SONET signal, that is STS1, is equal to 51.84 megabits per second. Now we say that STS1 because that STS1 is nothing but a synchronous transport signal, that is synchronous transport signal here, and that basic signal is about STS1 we use here, even if it is say that basic structure of STS of an STS1 SONET frame. One is about your basic signal. It has a signal is of a n signals are there, even a synchronous transport signal, because a SONET will transmit a multiple signals, or we can say that whatever the SONET frame we say, it consists of a STS n dash n signal there, and it has a bit rate equal to what we can say that n times of this is a 51.84. Suppose STS2 will be there, so 2 into 51 point. If STS3 is there, likewise. So that is about the bit rate for these frames are depending upon that what will be the number of signals used to modulate and a optical signal or a optical source. So that's why we say that instead of STS1, we need to say that in terms of logic, we say that STS-N signal. And that signals is transmitted. If you see that we have seen that a optical network layer, so in which we say that that physical layer of optical signal that is to be transmitted, or conversion of that electrical to the optical conversion, is nothing but the physical layer of a optical signal. And that physical layer of a optical signal that convert that electrical to optical conversion, so we can say that that becomes a optical carrier OC, that is OC dash N. Now here again the N stands for what will be the number of signals to be converted there or for a given particular carrier there. So generally we use that word OCN, STSN. So that is about how much n is nothing but a number of signals to be transmitted. Now we say that SONET oblique SDH. SONET is the standard used by the America here, and SDH is the standard used by the all other world people. Now in that case, so both the word SONET dash n or STH1 both are the same. But in the case of, so instead of speaking SONET, you can speak out about the SDH also. But that SDH is nothing but that it is equivalent to the STS-3, or we can say that it has the transmission bit rate of 155.52 Mbps, and that is nothing but what, a STS-3 is nothing but the SDH level 1. So that's why we can say that it is nothing but a synchronous transport model. We can say that STS1 is nothing but a S sorry STS3 is nothing but the SDH signal, and that SDS is nothing but what, a synchronous transport model. So that's why at that particular third level of STS1 we say that it is about a STM, synchronous transport model, and that rate of this, it has a price of this STS1. So that is 155.52. So that's why for the higher rate, instead of a SONET, we can say that SDH is to be used, and it is to be designated as a STM1. That is for the higher rate. STM-1, STM-2, or STM-M. Okay. N we have used for the label STS-N-N. Similarly, you can use that STM-N for this label here. Okay. Instead of using STM, okay, so we can use a n also, or a dash m. That m is nothing but the integer, or here stm dash m. M is nothing but the integer. So in which we use that m is equal to 1, 4, 16, and a 64 here. And that signal is equivalent to the SONET optical carrier dash n, where n is equal to what? A 3, because it is multiple of a 3, so that's why it is about a 3, 12, 48. Okay, likewise. And so that's why that SDH is nothing but STM dash N, in which we have the optical carrier consists of that N is equal to 3M. Okay, so thrice of M. Okay, so likewise we can say that. So there is about a common, you commonly use a signal format, that is a SONET M or a SONET N format here. SDH, sorry, SONET N format, that is STS-N format, or a SDH format, in which STM-M it is to be used here. Now in this case, if you see here, for this we are using that a 90 column, and out of this particular 3 column we say that that is about a section and line, that is it is nothing but interconnection between the load here, that is about a network connecting, or it is it carries the information for this given network. And then whatever the remaining column in that SONET frame, that is about the 8, we can say that 87 columns. So out of that 87 column, we can say that that is nothing but one column is used by the path overhead, and this all these 87 column is nothing but, we can say, it is called as a synchronous payload envelope here. So that is SPE here. And the synchronous payload environment, we can say that it consists of a path overhead, that is of a one column. One column is nothing but what, a 9 bytes. Okay, we can say that that is about a path overhead, and that path overhead is used to support the performance monitoring by the end equipment, that is the status, signal labeling, tracking function, and a user channel there. And this 9 path overload, again, that is used to locate the whatever the network or whatever the connection there, or what will be the connection between the node there. So that is useful for this path override. So using this path override, so we can considering this multiplexing of the SONET. So in that case, we can use a odd drop multiplexing for the individual information of the channels in that optical network there. And we say here it consists of this particular frame consists of this a 90 columns of byte, and that about the duration of this 125 microsecond. Now the similarly we can say that here a SONET STS-N format. Okay, same thing is here. We have the NT into N, and it has a column of a SPSN. So that is about the here we can say that 19 here we can say that 90 into N columns. That is about SGS-N SONET format. Here instead of that 90 into N, we can use the 90 into 3. So that will be STM-S. Okay, that is about 270 into N. So that is a STM-S SDH format. Okay, even you can say STM-M or dash. Okay, that is a thrice of that STS one. Then, if you consider here what will be the number of rows and all, 90 instead of 90, it is a 270 here, and that section line and a overhead it consists of 3 into N, but here it is consists of that 9 into N, and SP is consist of it 261 into N here. Now then how that connection is to be taken place here, that is about the network or a we can say that a connectivity between the two nodes here. So now if you consider that here we can define a SONET oblique SDH ring, and using that architecture we can say that the path between the given node to communicate, or a loop between that node to communicate the from one node to the another node here. And that is nothing but what we can say here is that a SONET oblique SDH ring, and we say that a path from node to another node, that is nothing but in that given ring 1 2 3 4 here it is nothing but a ring, and here is about the path to connection in a unidirectional connection connectivity or a bidirectional connectivity. So there are the standards used to connect the two network here, and for those standards, so that node will communicate to the another node in a unidirectional manner, or we can say that it has only a single fiber and they are communicating in a two-way, or it has a two fiber or a four fiber, they are connecting in a unidirectional or a bidirectional. So there are a lot of architectures are there, and out of which we will consider that a two fiber unidirectional path switching ring, and another is about we can consider that here another network we say that a two fiber or a four fiber bidirectional line switch ring. Okay, now here we can say that that's about a two fiber bidirectional, or you can say that a four fiber bidirectional likewise. So now in this case here, it is about a two fiber unidirectional path switching ring network that is communicating to the node here. Now if you see here, node 1 want to communicate to the node 3. So in that case, it will take a path, primary path of 1 and a 2 here to communicate to the 3. That is a unidirectional path. But when node 3 want to communicate to the node 1, then they have to take the path that is 3 to 4 likewise. That is about the unidirectional communication there. But the drawback of this one is what? If supposed to be any node fails, then how we can communicate to this one node to the another node? So in that case, what happen here? Suppose any node fails here, and in that particular case, so that node fails means what? That particular transmitter and receiver fails here. So now here it is about the traffic flow from node 1 to node 2, node 2 to node 3 here. Now it is receiving. likewise, and then it is transmitting likewise. So this is about the path here. So supposed to be this is about a primary path we are saying. If supposed to be this path failed, so in that case a protection path is used here. So to communicate from node 1 to node 2, node 3, we will use this protection path. Here we are saying that this is about a primary path 1, 2, 3 likewise, and this one is about a protection path. Okay, so now if supposed to be any node fails in between the ring, then protection path is used to communicate from one node to the another node. In the another case, that is about the architecture. If you see here, so we have the a architecture of a four fiber bidirectional line fixing network. This one is about a bidirectional from node 1 to node 2, from node 2 to node 1. So likewise, so we have a communicating from the node 1 to node 3 here. So path is to be used, that is 1P and a 2P for communicating 1 to 3 here. Okay. So now in the case of communicating from node 3 to node 4, we can use the because it is a bidirectional one, so we can use that 7P and a 8P. Okay, that is about a path. This is about a one path, second path, likewise. So we can use. But in supposed to be, this is about a bidirectional one. Means we can say that you need this one, then 2, and then node 3. Okay, this is a communication from 1 to 3 here. Again from 3 to 1, likewise. In the case of any node failure occur, so in that case, so here a protection switch network is used. Okay, likewise. So that will break, suppose any break in a fiber, primary fiber, or suppose there is a failure at that particular node. So in that case, that switching network is it is that node is a shorting here, and through that they are communicating. Okay, because we have the another path is present, so that is called as a reconfiguration of a four fiber PLSR under a transmission line failure. Okay, if supposed to be any network fails, so in that case, that protection is to be used to transmit the signal from the one node to the another node. Then this one is about a break in a cable, or if supposed to be complete fiber cable break here. Okay, cable failure. Now because it has, we can say that because it is a two directional there. Okay, any of the fiber breaks, so then in that case we can use. But in the case of if supposed to be complete fiber break cable breaks, then how this 1 to 2, 1 to 3 nodes and 3 to 1, 5, 1 is communicating. So in that case, if that node 3 is a fail here, okay, so in that case, so it is about a one loop is there inside that particular node. So that loop is called as a protection switching loop back. If that node failure occurs, so then signal from that node is nothing but a it creates a loop and it will be returned back there. So that is called as a protection loop here, or supposed to be any node fail. So in that case, they are using the in that particular SONET ring, they have a protection switching loop backs is used. Then how your SONET or SDH networks looks like. So these are the commercially available network architecture, and if you see here, so it has a point to point link, it has a linear change. Okay, point to point links from one to then it has a linear change there, it has a unidirectional path switch ring as well as a bidirectional line switch ring. This one is about a PLSR, this is about a unidirectional one, and it has the interconnected rings likewise. So means here it is the word OC192, that is a OC means optical channel dash 192, that is N, instead of N we are using that 192 here. And if you consider here the PLSR bidirectional, okay, in this particular case here, bidirectional line switch ring. So it has the interconnected ring, so in which OC192 two channels are there, and here we can say that it has a A4 fiber. Now that a ring consists of how many number of that OCN channels are there. So means this ring is interconnected between that OCN channel. So that is about a means total overall network. If you consider here, it has a large number of a channels connected in that particular ring or in that particular OC OCN channels there. But in the case here, we say here that is a OC 192, OC 48. Means it has a 192 channel, it has a 48, it has a OC 3. Now, if you consider that here, the capacity for this OC 42, or we can consider here in the case of OC 12, okay, as compared to the OC 12 and okay, and OC 48 now it is connecting now. So in that case, we can say that OC 48 ring it has a lower capacity localized to the OC 12 or a OC 3 ring, or we can say that a linear chain connected to this particular OC 48 ring, because it is connected from OC 12 to OC 48, means we can say that that network is connected to the extremely wide range of rates and a size of the given network. So that's why we can say that each of the individual rings has its own failure recovery mechanism as well as a whatever the management process is. Suppose we consider that in that case, so we can say that some of the ring fails here. So then what happened? So in that case, ring failure means what? Or number of channels in that particular network is depending upon that what multiplexing architectures we are using in that application. So that multiplexing architecture will add or a drop that number of channels in that OC-N network. So OC 192 is supposed to say here. So we can add that number of channels in that particular network there. So that's why we are using that a add drop multiplexer, and that add drop multiplexer, that equipment is fully synchronized. So likewise, we can say that here that OC48, that is OC-N we say, and that OC48 has a OC12 path. This is about a OC12 path, and dash dash is about a OC3 path here. Now that OC48, from this 48, it will drop this OC3 path and it will add this OC12 path, two path. Okay, means OC, it will add this two OC12 path and it will add one more OC3 path here. Okay, now it is a dropping, it is adding here. So that is called as a add drop multiplexer here. So means if you see here from this particular figure, one OC12, we can say that one OC12 channel and this three OC3 channels, okay, they are leaving and they are adding that a two OC12 channel and a one OC3 channel, and that is multiplex here because it is leaving this OC12 and adding the OC12. I mean that is nothing but what we can say, this one is a dropping and this one is nothing but a adding here. So that is about the add drop multiplexer. And then we combinedly we say that is about the OC40. Now here it is adding OC3 path. Okay, likewise. So it is dropping. This is about a added and a drop channels there. So that is called as a add drop multiplexer here. So that passing through the given particular network. So that is about a SONET add drop multiplexer here. This figure is saying a electronic add drop multiplexer for this SONET and SDH applications. Now we say that earlier wavelength division multiplexing means what? We are just combining the different spectral width and we are spectral signals and combining those signals and then we are transmitting. Now in the case of a dense wavelength division multiplexing, so we are combining the instead of a spectral signal, so we can combining the specific wavelength signal. So that is about, and that wavelength has a separation of a 1 nanometer, or we can say that a separation of below that 1 nanometer, and then they are combining here, and we are just here we can say that a combining. So that is called as a wavelength multiplexing. So that is called as a dense wavelength division multiplexing. Means we are combining the large number of a channel. Means we say that a S band or we can say that L band both are combined together and we are transmitting. So that is about we can say that a dense wavelength division multiplexing, and that is this example is about a DWM deployment of N wavelengths, that is about L1 to Ln wavelengths in an OC192, that is STM64. So it is 64 into 3, that is about STS level 1. So that means be the high or we can say that large capacity of this dense wavelength division multiplexer here. And this optical fiber that is used for that n number of multiple channels, and that is to be transmitted through the fiber in which we use a line optical amplifier, inline optical amplifier here, then preamplifier, then a demultiplexer. So that is about a dense wavelength division multiplexer. So for combining this particular multiple wavelengths here, for the given particular optical fiber, when we are combining all the channels, so at this particular input end of the optical fiber, they should have the sufficient optical power. If supposed to be that optical power is a large, so then there will be a scattering. If that optical power is a low, then we use amplifier and then we can transmit. So we need to use here specific optical power or sufficient optical power for transmitting the signal from one node to the another node here, or that is about a link here. Simple principle of optical add drop multiplexer here. This is about the wavelength L1, L2 dash Ln. That is about L1 to Ln. These are about the nth wavelength here. And it is removing that Li and K. Okay. And then it is adding that Li to K. So, and we'll get that L1 to Ln. Means that is about the adding here itself and dropping here. So in the given network, that adding and dropping is controlled by the network, and according to that only whichever the specific wavelength to be transmitted, that is to be transmitted through the network, and at some particular place that again we can add that specific wavelength in the given network. So that is about the adding and dropping the wavelength. So now here optical add drop multiplexer here, expandable passive optical add drop multiplexer architecture. In that case, these are the different wavelength band we supposed to be safe. Here that wavelength band, that is about we can say that is about the band 1. Okay, and this one is about the band 1 is adding here. So this is about the wavelength band 1 is dropping, this one is about the band 1 adding. So now in this case, one example of a reconfigurable optical add drop multiplexer. So in this case, these are about the optical wavelength, that is n wavelength. These are the drop channels from this. So to dropping this, here the coupler, or we can say that we can use a bragging device, or we can use the interference filter to remove those particular wavelength from this, or optical fiber, okay, optical filters to be used, so that we can use that particular channels to be dropped, and then the drop channels here, and then that signal is to be transmitted without that particular channel. And then this is about a wavelength blocker. Okay, that is about a channel. So see that what are the wavelengths to be transmitted, and it will block those wavelengths that is not to be transmitted here. Okay, then optical coupler. Then we can add those channels here to through this network, and then that only that particular wavelength signal is to be transmitted here. Okay, likewise. So that is about a wavelength configuring network. Again, another one is about a reconfigurable optical add drop multiplexer. So instead of that, we are using that switch, that is a 2 by 2 switch. That is nothing but a coupler, we say. That is about adding and dropping that particular wavelength channels in that particular optical add drop multiplexer. So that is called as a wavelength dependent. The switch is nothing but a wavelength dependent. That's it will drop that particular wavelength and it will add that particular wavelength. So that is about a wavelength dependent switching based reconfigurable optical add drop multiplexer. So how that switch is used, that is about the LK in, adding that word LK out, it is dropping that particular wavelength. So likewise, so this is about the connection between that add and a drop there. So that is about the add drop setting. Here is about the express setting. We can use that add port and a drop port for the given particular wavelength there. So instead of a 2 by 2 switch, we can use a 4 by 4 array for the add drop ports there. These are about the add port, we say. We can say that it is about a drop ports, we say here, and we'll get this output. These are about the mirrors, just like we say it is about a mirror. So in that case, there are the different components to be used to remove that particular wavelength or adding that particular wavelength. Okay, so likewise, output port here. Another example is here, wavelength tunable add drop device, and that is for the given particular wavelength. That is about a reconfigurable add drop multiplexer here. Or we can use a reconfigurable optical add drop, so in which we will use a wavelength switching network here. It is depending upon that what will be the wavelength. So means we can say that WSS is nothing but a wavelength selective switching. So only it will select a specific wavelength. Means that is nothing but what we can say. So L1 to Ln wavelength, lambda 1 to lambda n wavelength, and we are dropping that m wavelength here, and then adding those wavelengths, we will get that lambda 1 to lambda n output here. Again, we have the wavelength selective switches there. So in that case, we are using that variable optical attenuator. So it will attenuate those particular wavelength, particular signal, and then it is nothing but a switching network, and then multiplexer here. Likewise. So this one is about, another example is about the optical switching. In this case, we can say that input fiber 1 and fiber 2. These are about the optical splitting. Splitter means separating the different channels there. So that's why we require tunable filters for the separating the channels. Splitter means splitting the signal with respect to the wavelength. So it will use a tunable filter to separate out that particular wavelength. And these are about the switching matrix. And then we will add those particular channels here, lambda 1 to lambda 4, multiplexer here, and then we have a amplifier there. We'll get the filtered output. So this is about a optical cross connect architecture here, and according to that we can add the optical signal through this, or we can drop the optical signal. So this is about another structure is about optical switching network, and this is about a generic structure of an optical bus switching network. So in that optical bus switching network, so they have the different optical bus switching network, and in which they have the add drop separate channels or add drop that particular burst there. Okay, so this one is nothing but the architecture. Another is about a wideband DW network, and that can be configured through the any combination of a ring or a mesh network. So these are about a long haul interconnection here. We can use a reconfigured optical add drop multiplexer in through the metro ring, and this is about a access ring here. Then a wavelength division multiplexing, a network, how that optical fiber network looks like. That is for the long haul trunk cable contains a large number of high capacity single mode fiber. This one is about a multiple high speed DWM channel. You have here is the amplifier, multiple fibers per cable. This is about a optical fiber cable, and these are about the separating the different channels. Another example we say here is a combination, or we can say that a amplification concept for the operation in the C band and AF band. Means it is combining the both the band, that is a wide band network, or we can say that wavelength division multiplexing network. It has a lambda 1 to lambda n, that is the nth wavelength or a channel there, and then we use a specific amplifier for amplifying this particular channel there, a spectral band splitter. Means you can say that it's separating the C band and S band. Then in the C band, here the amplifier is used. This one is about a filter, that is a filter that is useful for the rejection of this particular wavelength. Okay, and then that signals are combined here, and we'll get that lambda 1 2. This is about a for the long optical network. Another architecture. These are all the example here to combine that how your signals are connected from a central office to the user premises. So that is about a central office, then a single feeder fiber. Here the multiple channels are combined, and that is separated here to the different, or we can say that distributions of the channels to the different users. And this is about the access region, that is about a premises, or we can say that distance between that whatever the central office or central communicating switching network to the user premises. And that is about a optical network we supposed to be see here. And